Hello everyone, my name is Iman. Welcome back to my YouTube channel. Today we're going to be continuing our lecture on thermodynamics, and we left off on objective 3. In this objective, we're going to discuss how energy can be transferred, specifically focusing on the first law of thermodynamics. Now, in the previous chapter, we defined energy as the capacity to do work or transfer heat. Now let's dive deeper into how energy behaves in thermodynamic systems. Now, the first law of thermodynamics, this is also known as the law of conservation of energy. This law states that while energy can be converted from one form to another, it cannot be created or destroyed. As a result, the total energy in the universe remains constant. This means that if a system loses energy, the surroundings must gain it, and vice versa. This is expressed as delta U of the system is equal to the negative delta U of the surroundings. Again, meaning that if the system loses energy, the surroundings must gain it, and vice versa. Any energy lost by the system is gained by the surroundings, and any energy gained by the system is lost by the surroundings, and the total energy of the universe is always conserved. Now, with that, let's begin to focus on how this applies to a system. The first law of thermodynamics, it can be written in this form: delta U, change in the system's internal energy, is equal to Q plus W, where Q is the energy transferred into the system as heat, and W is the work done by the system. Now, it's important here to note that this equation shows the internal energy change of the system, and it demonstrates that it depends on both heat and work. I also want to note that you might see this equation written as Q minus W, and that depends on how heat and work are defined in terms of their signs. But don't worry, both forms convey essentially the same information. For now, I'm going to stick to this form because we use this form in our MCAT general chemistry playlist, and I want this to be consistent throughout our lectures. I'll also define the way that we're going to set up our signs for both heat and work. But first, let's really break down what heat and work mean in thermodynamics. Heat is the flow of energy that occurs as a result of a temperature difference between two objects. Heat always flows from the hotter object to the colder object and never the other way around. Now, it's important to note a couple of things. One, heat is not the same as temperature. Temperature measures the kinetic energy of particles in a system. Heat refers to the transfer of that energy from one object to another. Two, heat is not energy itself, but rather one of the two ways in which energy can be transferred between systems. The other way is work. Work, again, is the second way energy can be transferred. In physics, work is defined as the result of a force acting over a distance, and the formula for work is that it's equal to the dot product between force and displacement, which can expand into force multiplied by displacement multiplied by cosine theta. Now, in the context of chemical thermodynamics, the signs for heat and work are determined from the perspective of the system. If heat is being added to the system, we're going to assign Q a positive value. If heat is removed from the system, then Q will be negative. If the surroundings do work on the system, work is going to be assigned a positive value. W is positive. But if the system does work on the surroundings, then work is negative. Keeping that in mind, let's go ahead and discuss a special type of work that often occurs in chemical systems, and this is pressure volume work. Many experiments, especially in the chemistry labs, are conducted in open containers under constant pressure conditions. When the system expands or contracts under pressure, we refer to the work done as pressure volume work. Now let us use an example involving a movable piston. If we exert a force on the piston, we cause it to move a certain distance, and we've done work. This is the same concept as applying a force over a distance, but now we consider the system's volume change. The work done in this case is given by this formula right here. Work is equal to minus P, where P is pressure, multiplied by delta V, where delta V is the change in volume. When a gas expands, delta V is going to be positive and work is negative, meaning that the system is doing work on the surroundings. When a gas contracts, delta V is going to be negative and work is going to be positive, meaning the surroundings are doing work on the system. Now here again, I want to note that you might have seen this equation, but with a different sign convention. You might have seen it as work is equal to just pressure multiplied by delta V without the negative sign. The sign of convention really depends on whether you are considering the work from the perspective of the system or the surroundings. The presence or absence of the negative sign reflects whether the work is being considered from the system's point of view or the surroundings' point of view. Both conventions are valid, but we just need to be consistent. And because I've described and explained this equation in the MCAT General Chemistry playlist using this convention, I want to be consistent across my videos. It's the same with our equation for the first law, where we said change in internal energy is equal to heat plus work. Now, keeping that in mind, the next thing that we want to do is we want to shift our focus to other common methods of energy transfer. For energy to be transferred between objects, they must be in thermal contact with each other. When heat flows between objects or within a substance, it can do so in three different ways: conduction, convection, and radiation. Each of these processes involve a distinct mechanism for transferring energy. Let's start with conduction. Conduction is the direct transfer of energy from molecule to molecule through molecular collisions. In solids, where molecules are tightly packed together, this is the primary mode of heat transfer. As molecules in a hotter part of the material vibrate more rapidly, they collide with adjacent, slower-moving molecules, transferring energy to them. Over time, this energy spreads throughout the material. So for example, when you place a metal spoon in a hot pot of soup, the heat from the soup transfers to the handle of the spoon via conduction, causing it to get warm. Metals in particular are excellent conductors of heat due to the mobility of their electrons. Next, let's talk about convection. This is the transfer of heat through the physical motion of a fluid, such as a liquid or a gas. This process occurs when warmer, less dense regions of a fluid rise while cooler, denser regions sink, creating a circulation pattern. As the fluid moves, it carries heat along with it. A good example of this is the heating of water in a pot. As the water at the bottom of the pot heats up, it becomes less dense and it rises, while the cooler water at the surface sinks. This cycle of rising and falling continues, distributing the heat throughout the water. The last thing we want to discuss is radiation. Radiation is the transfer of energy through electromagnetic waves, and it does not require any medium to travel through. So unlike the other two means of energy transfer, conduction and convection, which require direct contact between materials or motion within a fluid, radiation allows heat to be transferred even across a vacuum. So the warmth you feel from the sun on your skin, this is due to radiation. The sun emits energy in the form of electromagnetic waves, and this energy travels through the vacuum of space to reach Earth, to reach you. Objects that are warmer than their surroundings emit radiation, and then this energy can be absorbed by cooler objects. Now that we've covered how energy is transferred through different modes like conduction, convection, and radiation, let's move on to another key concept in thermodynamics, and that concept is heat capacity. Although heat and temperature are not the same, they are closely related, and we can use changes in temperature to calculate the amount of heat transferred. The quantity that links heat to temperature change is called heat capacity. Heat capacity is defined as the amount of heat required to raise the temperature of a substance by 1 degree Celsius. Essentially, it tells us how much heat a particular substance can absorb before its temperature increases by a specific amount. Specific heat capacity, this refers to the heat capacity per gram of a substance. It's the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. Molar heat capacity, on the other hand, this is the amount of heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius or 1 Kelvin. Now, if we know the heat capacity of a substance, we can use it to calculate the heat transferred during a temperature change. And this is done by this equation right here, where Q is the heat absorbed or released, M is the mass of the substance, C is the specific heat capacity, and delta T is the change in temperature. Now, in this equation, the specific heat capacity can be expressed in either Celsius or Kelvin because the temperature change, delta T, will be the same regardless of the unit used for temperature. This is why when we are dealing with changes in temperature, it doesn't matter if the values are in Celsius or Kelvin. Now, one important specific heat capacity to remember is that of water. The specific heat capacity for water is 4.18 joules per gram times Kelvin, or equivalently, this could be Celsius. So the specific heat of water, keep this value in mind. This means that water requires 4.18 joules of energy to raise the temperature of 1 gram of water by 1 degree Celsius or Kelvin. Now, this high specific heat capacity of water is crucial in many processes, both natural and industrial, because it allows water to absorb and store large amounts of heat without undergoing significant temperature changes. This property of water makes it an effective coolant and is also a reason why it plays such a vital role in regulating temperature in the environment. Now, to further explore the practical implications of these phase changes and the energy involved, we can further analyze heating curves, which graphically represent how the temperature of a substance changes as heat is added, highlighting the transitions between different phases. So we've talked about how we can calculate the heat absorbed or released using this equation right here. It's also important to know that when a substance is undergoing a phase change, the heat added or removed from the system does not result in a change in temperature. Therefore, phase changes occur at a constant temperature, and the temperature will not begin to change until all the substance has been converted from one phase into the other. Now, a heating curve allows us to observe these changes, and it is a graphical representation of how the temperature of a substance changes as heat is added. It provides a visual understanding of the phase changes and the energy involved in transitioning from one phase to another. Now, in a typical heating curve, the x-axis represents the amount of heat added to the substance, and the y-axis represents the temperature of the substance. As heat is added, the temperature of the substance increases. But during phase transitions, the temperature remains constant even though heat continues to be absorbed. This occurs because the energy is actually used to break the intermolecular forces holding the particles together in the current phase, rather than increasing the kinetic energy of the particles, rather than increasing the temperature. So for example, let's consider heating a solid substance. Initially, as heat is added, the temperature of the solid rises until it reaches the melting point. At the melting point, the temperature remains constant while the solid absorbs heat, and this energy is used to convert the solid into a liquid. The amount of heat required for this transition is the heat of fusion. Then once the solid is completely melted, the temperature of the liquid begins to rise again as heat is added. When the liquid reaches its boiling point, then the temperature again remains constant while the liquid absorbs heat that it's using to convert from liquid to gas. This is represented by the heat of vaporization. After the liquid has completely vaporized, any additional heat will increase the temperature of the gas. Now, the key takeaway from a heating curve is the distinction between temperature increases and phase transitions. Temperature increases is where the substance remains in the same phase and its kinetic energy increases. These are the parts of the curve where we see temperature increase. This is in contrast to phase transitions where the substance changes phase and the energy is used to overcome the intermolecular forces rather than increasing temperature. These are the portions of the heating curve where that occurs. Now, the total amount of heat required to heat a substance through different phases, it can be calculated using different formulas depending on whether the substance is undergoing a phase change or simply increasing in temperature. For the segments where temperature increases, so this part right here, this part right here, and this part right here, we can use our equation Q equals mc delta T. All right, Q is the heat added, M is the mass, C is the specific heat capacity, and delta T is the change in temperature. So for the portions of our heating curve where temperature increases, we can calculate the heat change using this equation. What about the parts of our heating curve that occur during phase transition? So this part right here and this part right here. To calculate the heat change, we can use this equation right here, Q equals mL. Q is the heat added, M is the mass, L is the latent heat. This is the heat of fusion or vaporization. Now, specific heat capacity and latent heat are properties specific to each substance and phase, and they determine how much energy is required for temperature changes and phase transitions, respectively. With that being said, let's go ahead and tackle a practice problem. This problem says silver has a melting point of 962 degrees Celsius and a heat of fusion of approximately 1.05 times 10 to the 5 joules per kilogram. The specific heat of silver is 233 joules per kilogram times Kelvin. Approximately how much heat is required to completely melt a 1 kilogram silver chain with an initial temperature of 20 degrees Celsius. So we have our chain here starting at 20 degrees Celsius. We're going to have to heat this up to the melting point, and then at the melting point, the chain is converted to liquid. So we need to calculate the heat that is required for each of these segments. For this segment where temperature is changing, we can use our equation Q equals mc delta T. And for the segment where our temperature stays the same, we can calculate the heat using our equation mL, where L is the latent heat. Let's go ahead and calculate the heat for this first part where the temperature is increasing. We know that the mass is equal to 1 kilogram. The specific heat capacity for silver is 233 joules per kilogram times Kelvin. And delta T is going to be final temperature minus initial temperature. So that's 962 degrees Celsius minus 20 degrees Celsius. That's 942. All right, and this is in units of degrees Celsius or in Kelvin. Remember, this is the difference in temperature. So it's going to be the same whether you just take the difference for the temperatures in Celsius, or if you were to convert them to Kelvin and then take the difference, you get the same delta T. And we're going to use the unit Kelvin here so that it cancels out properly with our specific heat capacity. We can go ahead and plug this into our equation. Q is equal to 1 kilogram multiplied by 233 joules per kilogram times Kelvin, multiplied by 942 Kelvin. All right, now notice kilograms cancel out, Kelvin cancels out. Our final answer is going to be in units of joules. Now, how do we go about calculating this? What I'm going to do is I'm going to round this to 200, and I'm going to round this to 1,000. So we have 200 multiplied by 1,000. That is going to give us 2 times 1, 2. And then we want to account for all our zeros, which are 5 zeros. 1, 2, 3, 4, 5. Our answer is 200,000 joules. So that is the heat required for this first part. What about for the second part? Here we can use this equation, Q equals mL. Q equals mL. M is still 1 kilogram, but what is L? This is given to us in the problem, the heat of fusion. That's going to be approximately 1.05 times 10 to the 5 power joules per kilogram. Let's go ahead and plug this in. 1 kilogram multiplied by 1.05 times 10 to the 5 joules per kilogram. This is a very easy multiplication. This gives us 1.05 times 10 to the 5 joules. Now, let's convert these to kilojoules and add them up. This is 200 kilojoules, and this is 105 kilojoules. And the sum of 200 plus 105 gives us 305 kilojoules. So the total heat needed, to melt the solid silver chain is going to be 305 kilojoules. And that's with our approximations. So with that, we've completed this example problem. Let's go ahead and move into our next topic. Having established the foundational concept of energy and the first law of thermodynamics, we can now explore specific thermodynamic processes that help us understand how energy and matter interact under different conditions. In thermodynamics, we often analyze how a system changes when subjected to different constraints. 4 fundamental processes, isothermal, adiabatic, isobaric, and isochoric, provide insights into these changes. So let's go over each of these 4 processes, starting off with isothermal. An isothermal process is characterized by constant temperature. In such a process, the temperature of the system does not change, meaning that any heat added to the system is precisely balanced by the work done by the system. And this can be visualized on a pressure-volume diagram as a hyperbolic curve. The reason for this shape is that according to the ideal gas law, PV equals nRT, for a given amount of gas at constant temperature, the pressure and volume are inversely proportional. Now, an example of an isothermal process is the slow compression or expansion of an ideal gas in a container that allows heat exchange with its surroundings. The system maintains thermal equilibrium with its environment, ensuring that temperature remains constant even as the gas does work on the surroundings or has work done on it. The next process we want to discuss is adiabatic. An adiabatic process is one where no heat is exchanged with the surroundings. The system is perfectly insulated. As a result, any change in the system's internal energy is solely due to work done by or on the system. Now, on a pressure volume diagram, an adiabatic process is represented by a curve that is steeper than that of an isothermal process. This difference occurs because without heat exchange, the temperature of the system changes as the gas expands or is compressed. So for instance, when a gas expands rapidly in an insulated container, it does work on the surroundings, causing its internal energy and temperature to drop. On the other hand, rapid compression increases the internal energy and temperature of the gas. This principle is evident in the phenomena such as the compression stroke in an internal combustion engine or the rapid release of air from a bicycle pump. Next up, we have isobaric. In an isobaric process, the pressure remains constant while the volume of the system changes. On a pressure volume diagram, this is represented as a horizontal line, indicating that the pressure does not vary even as the volume increases or decreases. During an isobaric process, any heat added to the system results in a change in internal energy and work done at constant pressure. Now, a typical example is heating a gas in a piston that allows the gas to expand or contract while maintaining constant pressure. Then last, we have isochoric. An isochoric process occurs at a constant volume, meaning no work is done by the system since the volume does not change. This is represented by a vertical line on a pressure volume diagram where the volume is fixed and any changes in pressure result from changes in temperature or internal energy. In an isochoric process, any heat added to the system directly changes its internal energy, leading to a change in pressure. Now, an example of this process is heating a gas in a rigid, non-expandable container, such as a sealed canister. As the gas is heated, its pressure increases because the volume cannot expand to accommodate the added energy. Now, let's go ahead and tackle a quick practice problem. This problem says a gas in a cylinder is kept at a constant pressure, 3.6 times 10 to the fifth power pascals, while 300 kilojoules of heat are added to it, causing the gas to expand from 1 cubic meter to 1.5 cubic meters. Find the work done by the gas and the change in internal energy of the gas. So the pressure is held constant throughout the entire process, so the work can be found using the equation work is equal to negative P delta V. Now here, we know our pressure. It's 3.6 times 10 to the fifth power. It has units of Pascal. And we know that the volume is expanding. And the change in volume is going to be our final volume, 1.5 cubic meters, minus our initial volume, 1 cubic meter. Now this difference gives us 0.5. In other words, 1/2. So we're essentially taking this value and dividing it by half, and that gives us our value for work. It's equal to negative 1.8 times 10 to the fifth power joules. Now this is our work done. Remember that the gas is expanding, and in our frame of reference, the system is doing work on the surroundings because the gas is expanding. Now, the next part of this problem is asking us to calculate the change in internal energy, and we can do this from the first law of thermodynamics, which says change in internal energy is equal to heat plus work. We're given our value for heat, 300 kilojoules. Now I'm going to change that to units of joules, so it matches with the units that we just calculated for work. The heat is equal to 3 times 10 to the 5 joules. And then we're going to add this to the work we've calculated, which is negative 1.8 times 10 to the fifth power joules. Essentially what we have here is 3 minus 1.8, which is equal to 1.2. And then we're just keeping the same units here, times 10 to the 5 joules. So our change in work is equal to negative 1.8 times 10 to the 5 joules, and our change in internal energy is equal to 1.2 times 10 to the 5 joules. And notice how we used both our equations that we've covered in this lecture to solve this problem. With that, we can actually move into our last and final objective for this chapter. And here we're going to discuss the second law of thermodynamics as well as entropy. Entropy is a fundamental concept in the field of thermodynamics, and it provides a measure of the disorder or randomness in a system. It's represented by the symbol S. The second law of thermodynamics, it states that in any natural process, the total entropy of a system and its surroundings always increases. This is sometimes referred to as the principle of increased randomness or the principle of maximum entropy, meaning that systems tend to evolve towards a state of maximum disorder. So for example, if you have a gas confined in one part of a box, then you remove the barrier, the gas molecules are going to spread out and fill the whole box. And that is because that state is more disordered. It's a higher entropy state. Entropy also has implications in the distribution of energy. In a higher entropy state, energy is more evenly distributed, whereas in a low entropy state, energy is more unevenly distributed. In short, entropy is a measure of the spontaneous dispersal of energy at a specific temperature. How much energy is spread out, or how widely spread out energy becomes in a process. And the equation for calculating the change in entropy is this one right here. Change in entropy is equal to Q rev. This is the heat that is gained or lost in a reversible process divided by T, which is temperature in Kelvin. Now, the second law, it has been described as times arrow because there is a unidirectional limitation on the movement of energy by which we recognize before and after, or new and old. For example, you would instantly recognize whether a video recording of an explosion was running forward or backward. Another way of understanding this is to say that energy in a closed system will spontaneously spread out, and entropy will increase if it is not hindered from doing so. Remember that a system can be variably defined to include the entire universe. In fact, the second law ultimately claims that the entropy of the universe is increasing. And this is captured by this equation right here that says the change in entropy for the universe is equal to the change in entropy of the system plus the change in entropy in the surroundings, and this is greater than 0. Finally, I want to note that entropy also plays a role in determining the spontaneity of a reaction. The Gibbs free energy change, it dictates whether a process is spontaneous, and it is related to the entropy and enthalpy changes, as the equation states that the change in Gibbs free energy is equal to change in enthalpy minus temperature multiplied by change in entropy. Now, I go into a lot of details in this about this equation in my MCAT general chemistry playlist, so if you need a review, go there. But really briefly, for a process to be spontaneous, delta G must be negative. A positive entropy change contributes to a spontaneous process as it drives the system towards greater disorder and energy dispersal. However, it is important to note that it also depends on other variables like temperature and enthalpy. Now, with that, let's go ahead and tackle a practice problem before we wrap up the chapter. This problem says if in a reversible process, 5.46 times 10 to the 4 joules of heat is used to change a 200 gram block of ice to water at a temperature of 273 Kelvin, what is the change in the entropy of the system? Note that the heat of fusion of ice is equal to 333 joules per gram. Now we know that during a phase change, the temperature is constant. In our case, for this problem, that is 273 Kelvin. Now, from that given information, we can actually calculate the change in entropy because the change in entropy is equal to Q rev, this is the heat that is gained or lost in a reversible process, divided by temperature. We know both of these variables. It's going to be 546 times 10 to the 4 joules for the heat that is gained or lost in this reversible process, divided by temperature, which is 273 Kelvin. This gives us a change in entropy that's equal to 200 joules per Kelvin. Now, the amount of heat that's added, we want to know if it exceeds or does not exceed the amount needed to completely melt the block of ice. We can go ahead and calculate this using this equation that says Q is equal to mL, where m is the mass, 200 grams, and L is the latent heat. So here the heat of fusion for ice, which is equal to 333 joules per gram. This gives us Q that is equal to 6.66 times 10 to the 4 joules. The amount of heat added did not exceed the amount needed to completely melt the block of ice. Therefore, no heat was applied to change the temperature of the resulting liquid, and the temperature remains constant. And with that, we've completed our last and final example problem and our last objective for this chapter. I really hope this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.